Okay, so in a previous video we looked at the half-wave sort of version of a phase-controlled converter. So basically we took the half-wave rectifier that we had in the diode case and we replaced the diode with a thyristor or a silicon-controlled rectifier, and essentially it gave us a semi-controllable converter. So here what we're going to do is we're going to look at a full-wave version. Sorry, I've cut off the top here. A full-wave version, which is the bridge rectifier implemented with thyristors. So what do we have? We have the same standard bridge setup. We have 1 and 2 here. These are going to be diagonally pairwise conducting. 3 and 4, same thing with them. They're going to be pairwise conducting. We also know that 2 switches in a single arm can't conduct at the same time, or leg, I guess you can call it. I don't know how you would, I guess technically both. But let's say 1 and 4 can't conduct at the same time, 2 and 3 can't conduct at the same time. And we know that I4 will be the same, IG1 and IG2 will be the same. We're modeling the load condition here as a constant current ID because we don't really care what's happening out there. As long as we have a constant current, we're happy. So if your load is such that you can't have a constant current, you would apply some filtering or have something in place that would make it constant. That's the assumption we have here. It might vary slightly. The model would change slightly, but overall the concept stays the same. So the half-wave rectifier is not very useful. This is why we go into the full-wave rectifier case, and the bridge rectifier is the most common configuration of the full-wave case. So the full-wave is a much better circuit overall. Okay, so what we're going to do is we're going to look at some waveforms, because waveforms really tell us what's going on. So these are the waveforms we have here. Vs is obviously the source voltage here. I haven't labeled it explicitly here, but this is Vs, okay? Vs is that voltage there. So we see it goes between positive Vs and negative Vs. It's a sine wave. It's positive between 0 and pi, and it's negative between pi and 2 pi. Okay, we also see that Ig1 and 2 is the same pulse, and Ig3 and 4 is the same pulse. That's because they're diagonally pairwise conducting. Also, we see that Ig1 and 2 are basically, that pulse takes place between 0 and pi, and we see that Ig3 and 4 takes place between pi and 2 pi. So the reason behind this is because, remember, in the case of a full bridge rectifier, you have Q1 and Q2, or whatever the top left and the bottom right diode would conduct in the positive half cycle, and then the top right and the bottom left conduct in the negative half cycle. So you want to have that same operation here, but you just want to be able to control the average, basically, of VD, and that's what we do here. Something that you'll notice here, you may or may not have noticed it, but I'll point it out. This voltage goes negative. This wasn't true in the case of the full wave with the diodes. That, in that case, would always go to 0, and then the diodes would change states. The reason this goes negative is because current doesn't switch from one pair of devices to the other until the other device turns on, right? So what happens is, despite the fact that this voltage crosses 0, these diodes will continue to conduct, and they will only change states once the other diodes are turned on and they force the other two diodes to turn off. So these two diodes will, let's say you had 1 and 2 on here, so 1 and 2 are on up till this point. It crosses 0, they stay on during this time. Then at pi plus alpha, because you want it to be symmetric, so you want to have some type of regularity to your switching. So you have the same angle alpha here after pi, and you do pi because pi is when it goes negative, and that's when the other two would start to conduct. So you apply this pulse at pi plus alpha, and you'll notice right away what happens is instantaneously you have this sort of change. Okay, so the current starts flowing to the other two devices at that point, and so it does that for the entire negative cycle, and then you see the same thing happens here again. So this 2 pi plus alpha is basically the same condition as this initial alpha. That's why it goes negative in this case, and it doesn't in the other case. So the pair of diodes conducts, and they turn off by the action of the other pair turning on. So any conducting pair is only forced to turn off when the other pair turns on. If the other pair doesn't turn on, then the load current must continue to flow in the first pair, and it'll keep that diode pair on, because you have to have some type of, if this is a current source, this has to be a continuous path for it to flow, right? And so that's what you kind of have in this situation. What we can do now is we can write the average voltage, right? Because that's what we're interested in. And we can write the average voltage based on the function we see here in front of us. So we know that VD average will equal 1 over pi, because this is periodic with pi. This will be alpha, and this will be pi plus alpha, because we know it's periodic, and every time after that it'll just be the same waveform again. So this will be Vs sine omega t d omega t, and if you solve this you'll get 2 Vs over pi cos alpha. Okay, and so this is the voltage as a function of alpha, basically, right? So this is the output voltage, and it varies with alpha. Now we can look at a plot here, right? So what we're going to do is we're going to take a look at the they call this a sort of control characteristic, and so we have this condition here. So this is the output voltage, VD, the average voltage, and you'll notice here they've done this little bracket thing. So there's different ways that people usually refer to averages. We've been referring to averages with this sort of overbar. So let's stick with that, okay? It's the same thing, really. It means the exact same thing, but that's what you have, okay? And so in this case, they're normalizing this plot, or this plot has been normalized, in order to compare it to the case where you're using diodes, right? So VD0, or VD0, I should say in this case, VD0 is equal to 2 Vs over pi, which is what the average output voltage is for a full wave rectifier, and that's without any thyristors. That's with no phase shift, none of this alpha business. It's all just diodes, right? And so that is that's one extreme case that you have. And so here we have this alpha, and again, alpha is this firing angle. So this thing we call the firing angle, and the firing angle, that looks kind of like a Y, doesn't it? It's angle. So the firing angle is basically the difference between where a normal full bridge based on diodes would change its states, basically, or would start conducting, right? So this in a full bridge, full wave, whatever you want to call it, rectifier with diodes, this time would actually be at 0, and this one would actually be at pi, and this one would actually be at 2 pi, but you have that alpha, that's that sort of delay that they have there, right? So you'll notice something interesting about this one relative to the half-wave case. And in this case, you'll notice that this voltage characteristic goes negative, right? So between pi over 2 and pi, this thing goes negative. Now, what does that mean? So in this case, rectification, so this is the sort of boundary here, I guess. So if we have this boundary between of rectification and inversion, in this case, what's happening? Power is flowing from AC to DC. And in this case, power would flow from DC to AC. Now, there's a bit of a problem here because, I mean, this is what happens in theory. When you apply negative voltage and a positive current, you would have power flowing in the opposite direction. Or you can have a negative current and a positive voltage, whichever way you look at it. That's fine. So here you see this is negative. So this ratio becomes negative, meaning the average output voltage relative to whatever the benchmark case is, which is this VD0 here, that voltage is negative, but the current is still positive, meaning the power flow has been reversed. That's what we see here. So you see here in quadrant 4, voltage is negative, current is positive, right? You can't have that case in this configuration like this because of the way that these are oriented. So you'd have to reverse the direction of all of the switches here, and then you can have inversion. So although theoretically this is what happens, technically you wouldn't be able to achieve that state. So only the AC to DC power flow is allowed, otherwise you wouldn't have any conduction in these switches. Okay, so again, I won't go through the process of how that works, but if you were just to imagine, for instance, that you applied a negative voltage here and you were to actually go through all the switching states and such, you would find inconsistencies like the kind we've seen when we were discussing half-wave rectifiers, and I guess we did it for the full bridge too, and we looked at inconsistencies based on the method of assumed states. So again, I'll link all the videos to the diodes and all that stuff in the description, so you can look at how we've developed all these concepts, because really jumping in at this point there's probably a bunch going on that we've already discussed previously, so it'd be better to go back and watch those videos. So another thing we can do is we can take this one step further, and we can look at the concept of phase control, but with an AC side reactance. So we did this with the full bridge as well. We called it the commutation reactance, right? So what we're going to do is we're going to have a voltage source, and there's going to be a series inductance, and this is usually something very normal and very much expected in a practical system. You expect to have some inductance, whether it's large or small is a different story, but you almost always will have some, oh, I forgot the switch there. You will have almost some inductance, no matter what you do, whether it's a power supply's inductance, whether it's like a transmission line, anything. It could be a filter of some sort, but those things will impact the operation of the circuit. So we have here this circuit again. These are all SCRs, so they have their gates. And again, what I'm going to do here is I'm just going to assume that there is some current. I don't care what the current is. I don't care what the value is. I just care that it's some constant ID. And I'm going to have a voltage here, VD, and that's going to be Vs sine omega t. And I'm going to call this thing here LC, as we did in the past. Okay, and I'm going to call this thing here IL. Okay, I'm not going to label the switches. The switches are labeled in the same manner as they were before, but basically the effect of the AC side reactance is the same in the SCR case as the diode case, except the commutation process will be delayed by an additional angle of alpha. Okay, so if you haven't seen the video where we looked at the initial AC side reactance with the full bridge, I would highly recommend you do that because that's where we explain everything. We'll go through some of the details here as well, but a full discussion in depth was done in those videos, so you can have a look at those as well. So basically what happens is we have more waveforms. So let's take a look at this waveform, okay? So this is a sort of simplified couple of waveforms. What we're going to do is, and by simplified I mean we're not looking at a whole bunch of different things. We're looking at the output voltage and we're looking at the input current, okay? So we know that the current, well, in the standard case, the current would be more of a square wave, right? Because you would have the current would be positive, and then it would be negative depending on whichever direction or whichever pair of diodes were, I guess diodes, well, even SCRs, if you had this case, for instance, you would have a sort of square wave current. Here, in this case, what you do is you have these sort of slopes and these curves, and it's not just flat, right? So what's happening is basically during commutation, and commutation is this time u, okay? So this time here is defined, or well, not time, I guess it's a phase, right? So this point here is defined as alpha plus u. That means this thing here, this time where the waveform there is 0, this thing here is u, and that's the sort of commutation period or interval, whatever you want to call it. Okay, so that's how long it takes for the current to go from one pair of switches to the other pair, right? So it's not instantaneous. So in this case, I mentioned that you have this voltage goes below 0, and then you apply a pulse, and then all of a sudden the thing turns on, right? So you apply the pulse, and it turns on instantly because there's no inductance. The inductance, nothing forces or nothing delays the change, right? So the switching of the pairs instantaneously converts or translates or makes the current commute from one branch or one pair to the other. It's instantaneous here. So this switches on, this happens. But you'll notice here, well, what you would see is alpha is where the switching would happen. So you would apply a pulse here, right? So if you apply a pulse here, let's say, this is where the pulse is applied. Again, the duration of the pulse is not so critical. It's just that a pulse should be applied there. You apply a pulse at alpha, and that's when it causes this current to go up. But then it requires this time here. See, IL goes from minus to positive during that time. Well, during the time where this is 0. And maybe I shouldn't technically draw this to be the same duration. Otherwise, that might make you assume that it should be the same duration. So let's make it smaller. Okay, so it's a very small pulse, but it is applied nonetheless. And what happens during that time is this current has to ramp up from one extreme to the other, and then it would stay constant during that time there. And so you see that during that ramp up time, that time where it's changing, all 4 switches are on at that time. Okay, and that's why VD ends up being 0. So that's the sort of commutating effect. And the commutating voltage is therefore the voltage that is applied in order for this commutation to take place, or the voltage that is applied to the inductor while this commutation is taking place. Because if VD becomes 0, then that means the voltage across this inductor, we can call it, let's say, VL, right, will be this Vs source voltage minus whatever's on this output here. Well, again, assuming those are conducting. But if all of these are conducting, basically you've applied only Vs there. So Vs is the commutating voltage. And the commutating angle can be found by the inductor, right? So how do we do that? What we can do is, we know that in an inductor, the voltage and the current are related by the inductance. And you can integrate then, so you know this sort of VL equals L di by dt, right? This is the equation that everybody should be familiar with, okay? So if you expand the time scale, you have deltas. So you have delta I, and then you might have a dt, or you can have whatever change in current. However you want to model this, you can do it that way. So essentially, if I simplify this, I can say that the change in current is 2ID, okay? Because it goes from minus ID to positive ID. That's what this waveform here is showing me. It goes from minus ID to positive ID. So that's 2ID. And then I know that this L, I mean, really it's going to be omega L in this case because we're thinking about this in terms of a sort of complex domain. Well, not even complex, we're thinking about the reactance, right? So I shouldn't even say complex. We're thinking about the reactance. So we want to know what the effect of the reactance is because it's a commutating reactance, right? So 1 over omega LC, right, is what we're going to have there. And you're going to have, what's the applied voltage during this time? So the applied voltage, again, this will happen between alpha and alpha plus u. That's the sort of commutation interval, right? Between alpha is when this pulse is applied, and alpha plus u is when the voltage becomes non-zero, or when this current reaches its extreme, however you want to think of that, okay? So during that time, the voltage that's applied, it's a sine wave. I mean, it has to be, it's just Vs. So it's going to be Vs sine omega t d omega t, okay? Now if you solve this, well, first you solve the integral, then you'd have to rearrange and you'd have to solve for u, because u is this commutation period that we call. If you solve all this, you'll find that u is equal to cosine inverse cos alpha minus 2xcid divided by Vs minus alpha, okay? And again, you can go through and solve this. If you're not sure how to solve this type of integral and get to this type of situation here with this equation, go back and look at the other videos. I'll link them in the description with the commutating reactance for the full bridge. And we show how to do that. And this is just one step further because you also have this alpha plus u. So you have alpha here now. Before it was just 0 and u, right? In any case, you have this value of u. This is the commutating interval, however you want to call it. And you can then find the average voltage Vd, right? So Vd is going to equal Vs over pi, 0 to alpha. I drew the 0 on the wrong side, didn't I? It's okay, so let's get the 0 on the right side first. This will be minus sine omega t d omega t plus alpha plus u to pi, okay? And this is sine omega t d omega t. I should probably put brackets around there and around there as well, okay? And so what am I doing here? I'm trying to find what the average output voltage is, and that's this thing. And I know, so I know that between 0 and alpha, which is this purple, I guess we can try, is this purple part. That's the first part of the integral that I'm solving. Okay, and then the second part of the integral that I'm going to solve is going to be, let's use this pink color. So that's going to be this color here, this area here, okay? And so that's between alpha plus u to pi. That's the second part. So maybe we can put like a purple like this, and then we put a pink like this. So that's the pink part, okay? So that's what you have. Is that what I did? That's what I did. Okay, good. So you can then solve this, and you can get an expression that's fairly compact, I guess. I don't know. This is cos alpha plus cos alpha plus u. Okay? And we know that cos alpha plus u is equal to cos alpha minus 2xcid divided by Vs. What that implies is that this is equal to minus u, right? This second term is minus U. And so we hardly ever use U explicitly. Like we don't ever really need to determine what U is explicitly, right? So, and again, this relationship comes from this thing up here. Okay, that's the whole point of determining this thing here. So I can rearrange this entire expression and I can get this. So in any case, we hardly ever need to determine U directly unless like you want to find some characteristics of the converter or something, but you won't ever really need to calculate the value of U. Again, maybe in some cases, but we don't really need to explicitly know it. But the equation helps with VD, okay? And so how does it help with VD? Because in VD, we can substitute some stuff, and we can find that VD average is equal to 2Vs over pi cos alpha minus XCID divided by Vs, right? And so this is the average output voltage that we have. And you'll notice we've also, conveniently enough, and yes, this is obviously planned, this is VD naught. So this is the average output voltage of a full wave bridge rectifier when there's only diodes operating, right? And so now what we can do is we can take a look at this sort of, what did we call it? I think we called it like the conduction control characteristic, something like that. Whatever it is, it's a characteristic, okay? It's a characteristic of how we've done this incorrectly again, VD, of how the output average voltage relates to the benchmark case of VD naught, right? And you'll notice here that there's these sort of diagonal lines. You have 2 degrees of freedom kind of here. You have alpha, and there's also this U. U is not really a degree of freedom, but it's another sort of restriction that's imposed. And so this is, I guess, the load regulation characteristic. I mean, that's really what's happening here. I guess because the other case was a different thing, right? So this is a different thing than this. So I'm sorry that I shouldn't be comparing the two. Technically, this is different. This is load regulation. So this is telling us how the output voltage varies relative to the output current, because we see that obviously there's XID here, or XCID over Vs. So as the load condition changes, so too will your output voltage. So we see that as alpha changes, this boundary is also changing. So this lower region here is essentially they call it, I think, like a margin angle. It's essentially, it's a restriction. So you need to have alpha plus U to be less than pi in order to ensure that commutation takes place properly. Otherwise, if you don't, you might have commutation failure, as they call it, which may or may not necessarily be a bad thing, depending on the application. But essentially what it means is that your switches won't the current in the switches won't commute properly. And we won't get into too much detail about this, but what you do need to understand is that in a case like this, we see that the output current restricts, or well, I guess restricts, also the value of alpha does as well, restricts the range sort of over which this relationship takes place and how it's related overall. So there's 2 things going on here. One is ID. So as ID increases, the output voltage, the average output voltage relative to the benchmark decreases. And at the same time, as the value of alpha increases, this, well, I mean, the sort of the highest it can go, which is 0.5 in this case, becomes much lower, right? And it might get to a case where it's negative here. And that's, again, the inversion case, but you can't necessarily have inversion in some of these configurations like this one. But it's a theoretical limit nonetheless, okay? So we looked at here, I mean, we did quite a bit in this video, so let's take a look and recap. We looked at the full bridge, full wave version of the thyristor rectifier here. We saw that we switch in a pairwise manner, as we have previously, and we also saw that this output voltage goes negative, right? Even if momentarily. Again, this moment depends on what alpha is. But again, we said this happens because your switches, the conduction of your switches is dependent on the other 2 switches. So you have to force these to turn on. In the case of the diode bridge, they're forced to turn on by the voltage. Here, we have to apply a gating pulse. If we don't, these will just keep conducting and the other 2 will never turn on. Okay, so we see that these are pairwise here, 1, 2, and 3, 4. So this is 1, 2, 3, 4. And we see that this voltage goes negative. Then we developed an expression for the average output voltage, and we saw that it was dependent, well, I guess it could be related to the benchmark case where we have diode bridges as opposed to SCR bridges. We saw that this voltage can be positive or negative depending on the value of alpha, but we said that this negative case is not really achievable in this configuration, although theoretically it could be achieved, right? Because this expression is not unique to this situation. If you were to flip the switches, you would still end up with a similar equation, and you can then have inversion, which is DC to AC power flow. We then looked at the case with source inductance, any inductance on the source. It doesn't necessarily have to be part of the source, but it could be any inductance on the source side. And we saw that with the introduction of this source inductance, this current ramps up. So it takes time to go from minus ID to positive ID, meaning this current that's in, let's say, if these two were conducting, if the top left and the bottom right were conducting, then it would take time for the current to go from this pair into this pair. Okay, and that time we defined as U, which is why this goes from alpha to alpha plus U. And during that time, when that commutation takes place, or the current is switching from one branch to the other, we know that this voltage VD will be 0 since all 4 switches are conducting during that time. And so you have to be careful with controlling your switching pulses during this type of operation, of course, because you need to make sure that your switching is sufficient for all of these things to take place properly. We then looked at what this, or how to define this commutation interval, duration, period, whatever you want to call it. And we used a fairly straightforward method. We used this sort of Ohm's law for inductors, they call it sometimes. But really it's just, I mean, the voltage and the current are related to in the inductor in this way. And we saw that with that we can determine U, this commutation interval. We did a similar process for this in the full bridge case with diodes. So again, that will be linked in the description. So if you're not sure, we can look at that in that other video, and you can always ask questions in the comments and such. But we saw this U here, and then we used this U along with this expression for the average voltage to come up with something a bit more familiar. And the reason this is more familiar is because we have this term here, XCID, which is kind of sometimes referred to as a load regulation term. What it means is the output, well, we see very clearly because we can't see that here, right? So this expression doesn't tell us the same thing as this one does. But in this expression, in this orange box, it tells us very clearly that the output voltage depends on the output current, and that the output voltage will decrease as this output current increases. And that's what these lines show us. And then we have finally established that there is this thing called this, I think they call it the margin angle. Essentially, it's a limit on how far you can go before you'll have commutation failure. So the current will not commute entirely from one branch to the other. Again, it might be something desirable. It is in certain cases. It's not necessarily a bad thing. But for standard normal operation, it's best to, operate within these regions here. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.